Okay, everyone. So we are about to start the tutorial, and this is the topic of the tutorial: introducing deep learning models for emotion recognition and analysis. And as you heard, Professor Vijay mentioned about why do we need this domain of research and why we need to learn about this. So we will start, but before I will request my Professor Nagamani, to give a brief introduction about ourselves and what we do. And so let us begin with that, and then I will continue with my tutorial talk and we will start from the very basics of deep learning. Okay, how many of you know Python? You have actually coded in Python. All right, and have you guys you know Python? No. Okay, how about you?
I'm a software engineer.
Okay, that's great. And the rest of you, do you have basic knowledge of Python? Any idea and how? And also, do you guys know the basics of machine learning? Right? All right. So if you know, then it will be a bit easier for you. If you don't know, don't worry about it. We will go through it. We'll go through the very basics and then we'll go to the very advanced. We'll also go through the code. So we'll get to see a lot of code. We'll get to see how do we actually build one of these motion recognition models. So it will be fun. But before we start with the technical details, let's start with the introduction. Okay. So she's my professor. I will request my professor. She's on the Zoom call. I will request her to give us one introduction. Okay.
This is a tutorial about introduction of the deep learning and
Yes.
about the emotional the recognition with the deep learning is the basic. And it's this tutorial is basically to introduce the from the zero level of knowledge from this domain to a certain level of you can write a research publication kind of thing with your experiment. That was the thing. Okay, so this is the main motivation of introducing of this tutorial in this conference. Okay, yeah, before going to the introduction of the details of the tutorial and other thing, I would like to introduce myself and Shanknil and our university. The first, the University of Hyderabad is located in Telangana state in India, and this was a central university. And our university is a campus of 2,500 acres of place. Presently, it is 600 acres. And our university was the first university as introducing in 1980s, the introduction of the
It's not the
I would like to give university introduction. So maybe. So that's why our professors will have different domains of artificial intelligence experts and research happening. And our university has multidisciplinary, and so we work all integrated with the humanities, life sciences, the drug discovery. And recently in Corona period, we also have contributed tremendous the research in drug discovery kind of thing. And also it is a high performance, and we also have a strong mathematical background, and a professor of 100 years old, Professor Sierra, who is a statistician who is working mainly on language and technology. So that's why our university is strong in artificial intelligence till that deep learning. And most of our PG students, so you can see that the Shanknil is presently his post graduation. He's submitting his MTech. He submitted MTech thesis, and his Viva is pending. Okay, so they have a strong background in the domain of artificial intelligence and implementation of all the algorithms, methods, where we can see in progress of the artificial intelligence in terms of machine learning. And then now recently in 2015 onwards, the deep learning, because of the technical hardware support in entire world, become the easy. So the deep learning come into the boost kind of thing. So we thought the introducing of the deep learning in this, especially the our conference is a human computer interaction. the human emotions. Exploring the human brain is a different disciplines. Our conference is exploring. Every year they are introducing the new domain knowledge, and last year they introduced the music and cultural thing, which are the more natural emotional expression from the audio as well as the visual expression kind of thing. So that was the main background of this thing. And about me, I'm working in this university last 15 years in the teaching the field of artificial intelligence, software engineering, and my specialization is in speech processing and computer vision. So I also look into the embedded system, where my intention is to robotics, where we can incorporate human thinking concepts. The naturalness bring into the machines is the main motivation kind of thing. And my student about the Shanknil, he's Shanknil, can you just move the slide to your this? So the Shanknil is my PG student, and he did the 2 courses with me. While doing his course in operating system, he has published 2 publications along with the co-author of his classmates. And he was guiding and handling the interns, and also collaborated with the Professor Dhananjay sir in his lab kind of thing. And he's working on this thing, and he has presented a paper on implementing the neurozen, that is a kernel based neural network, the convolution neural network implemented for a speech feature extraction kind of thing. And he also participated in music context, where the emotional parameters need to be extracted with his develop the neural network tool kind of thing, and slowly moved. And his PG's project, he worked on completely exploring the deep learning methods and working on the GPU systems, and worked on the emotional parameter extraction. So his PG practice, the research work outcome, we thought we will present as a tutorial, and it will be given a chance for all the new upcoming researchers in the deep learning will be helpful with his expertise and experience kind of thing. Okay. Uh, this is about us. Okay. Maybe I have a note given complete the educational background and other thing. It's a series. We both are computers background, having the BTech and MTech, and I did my PhD in computer science. And hopefully Shanknil also have planning to do research in with a good professor guidance and other thing, in exploring the more on human health parameters of the emotions kind of thing. And he also has developed one tool where he want to create a natural database with the audio and video by developing a small mobile application to capture the audio data and video data kind of thing, along with the one of the intern student. This is about us. So let's go into the details of our tutorial. So our tutorial is mainly looking into the affective computing. What exactly? How many of you know about the affective computing? Am I audible?
Yes. I hope she's audible at the back as well. Yes. Okay. Yes, ma'am. Please continue.
Yes. Okay. So let's what actually the affective introducing the first term affective computing. So now everything we always the day-to-day activities and every minute or second we are interacting with the missions. As we take our lively body part kind of thing, physiological structure, the computing part also embedded in our system kind of thing. So every minute, every activity, we are interacting with the missions kind of thing. That means we want a mission to feel as our brain is feeling kind of thing. So that a mission need to capture the feelings or emotions of the human, and based on their emotions and the feelings and the other thing, so we can decide or we can predict certain conditions. Maybe in healthcare system we can see that what kind of emotions the people are expressing and what is their mental stress or maybe physiological health conditions kind of thing. We can predict and we can suggest them the health kind of thing. If it is, you look the same thing into the emotional predictions and other thing, in educational thing we can see the students feelings and their expressions towards the lecture and other thing, and based on their feelings and expressions and other thing, automatically we change the lecturing part. Because nowadays we saw that last 2 years we see almost online kind of thing. If we introduce the machines to be teaching as good as human tutor kind of thing, so the machine also need to see and feel and predict the emotions of the students and change the according to them their understanding and other thing, and recommend the subject or the level of the knowledge they need to gain kind of thing. So that way these effective computing is involved in everything. So you take it healthcare, the education system, entertainment, and many other, including the sports kind of thing. So it's a person based the caring system kind of thing is one of the important parameter of the effective computing. Is it clear? Okay. So these things, now we see that now effective computing is giving an opportunity for us to sense the uh, human feelings with the electronic components like sensors and IoT. Now we can say that the industry 4.0, all of you are understanding all this terminology, I hope so. Is it? The industry 4.0 and software engineering for 2.0 is promoting everywhere involvement of the artificial intelligence in processing, in building a model, okay, and in predicting the condition kind of thing. So these three terms, you see that the preparation of the data and the building a model and prediction, these are the major the building blocks of the any machine learning application kind of thing, right? So acquisition of the data is important. That's done by the sensors. What kind of sensors and how intelligence you making the sensors and other things is coming under the effective computing kind of thing. Now you want to make a model kind of thing. A model is a something you observe the parameters, and these observed parameters are giving a certain structure kind of thing. So this structure or the building block helping you to segregate or classify the things, right? Which is the basic building block of the pattern recognition part kind of thing. So now that when it comes to the pattern recognition part kind of thing, a machine is doing the pattern recognition. The human pattern recognition process is different because the human perception is more important rather than representing the data in the beginning. So both machine and humans are doing the two tasks, but the way they do process kind of thing is different. Humans always do perception and then try to interpret kind of thing, whereas the interpretation is the first coming into the machines, and then only we can do the perception with the method of an defined software program. That's a computing programming kind of thing. So these computing programming or the method, or you can call it as an algorithm, is represented. And in the beginning days, the people thought the artificial intelligence in around in 1980s, where the neural network concepts as boomed, and that was the thing. They thought that they can build a human mimic a machine kind of thing. But unfortunately, at that time, it was the computing facility was not good at that time. So that's why the upcoming the artificial intelligence and artificial neural network concept could not catch the world to make the human brain certain aspects. We cannot explore entire brain, the functionality, certain aspects of the brain they could not make it. So then slowly in again the machine learning has come, picked up slowly when it is the people are able to capture the data and process the things. Okay, and then the machine learning is something every time you need to represent, and then only it is able to do so certain things what the intuition, natural intuition of the human things could not capture, and we could not able to achieve the things. So then slowly the deep learning is coined in 2005 around. Maybe you can find very good research articles in 2005 by the Professor the Lee Deng, who is a Microsoft person who has incorporated these deep learning methods into the speech applications kind of thing. Then slowly, because of the machine capabilities is increased and storage capacity and other computing facilities like a cloud, fog, and all those things are the upcoming. Then a deep learning now become the one of the key role player in the computing facility, especially in the human computer interaction part kind of thing. So that's the main key part. So a deep learning is something, it's not the something like a wider kind of thing. So you can see that vertical kind of thing. Deep is an in-depth exploration of the features, and these features are representing to build a model kind of thing. That's the model is a certain algorithm and other thing which you are going to learn in this thing. If you see that the BERT is the bidirectional encoder a transformation of neural network, where it is extracting the it's capturing the all the features or emotional parameters of the human, and automatically it is able to predict kind of thing. Okay, so in this slide you can see that effective computing in various this thing. So here we just added, and we are sorry we could not include the reference um, acknowledge, and in the end we have acknowledged all the things. Okay, so these slides pictorial representation, because many of you are not aware of this terminology and other thing, and these slides are giving you a good opportunity to know what exactly the effective computing kind of thing. So this effective computing needs the process. That process is implemented by the deep learning, right? And in the deep learning, core part is the artificial neural network kind of thing. In this thing, the learning part, how human is learning, we cannot define the step by step kind of thing how human brain is learning kind of thing. Some of the things automatically it has done, because each person learning capability is different. Now this deep learning is helping the individual learning capability uh, feature mimic or simulating kind of thing in a mission, this thing. And now how we are going to implement this deep learning method, that means extraction of the features. See, normally in machine learning, everything you guide them. So it's like something like a class guidance, teacher guidance kind of thing is the machine learning, Whereas the exam writing by the student and other thing, when the new question paper, where the terminology and question paper is coming, students will automatically the capture the different learning concepts and other thing, and they are able to write the exam kind of thing, right? So it's you are not specifically externally defining the conditions how the data is extracted in the deep learning. That's a you can see a major difference in deep learning and machine learning kind of thing. Okay, so these things you want to implement with the mission. That is definitely you need to tell them in a proper language where the mission can understand kind of thing. So that exercise the Shanknil is going to take care. Okay, so the language here we are trying to make mission to implement the deep learning is a Python. So this Python is helping you pick up the appropriate methods. So these methods are represented by the libraries which already built well built algorithms kind of thing, and these are doing the process as you do in the mission kind of thing. So this tutorial mainly we give so that everyone can learn how a data can be captured, okay, with your programming skill of Python, and exhibit certain deep learning method, especially in the emotion parameters kind of thing. Because why emotions only we are highlighting here is that nowadays emotions is very important. You observe that in Corona period or pandemic period, the emotions, how it is affected to the human life kind of thing, and what are the parameters. And if you see that mainly the many of the topmost institutions, especially we observed in India, the topmost institutions, the young generation is unable to trace, understand their feelings and other thing, and taking the extreme steps kind of thing. And that's why the main parameter we are taken as a emotions kind of thing. These emotions, you see that in Indian tradition, in Vedas, they are well explained in terms of the rasas. And these rasa means the feelings kind of thing. And how many varieties of these rasas, and what is the causing these rasas based on the human physiological body. So they are well explained in theoretical part, that there are 6 chakras in body kind of thing. That means the pinpointed those things, and you can concentrate so that you can control the 72 lakhs of these nadis. Means the neurons can be streamlined and controlled, and then we can control our body and we can control the emotions, and that way we are taking care of the health, the aspects and human important parameters kind of thing is the main motto of this uh, tutorial concept. uh, with this I just hand over to the mic to Shanknil. Is it fine? Any queries we will address in the end of the this thing. Yes, Shanknil. Am I audible?
Yes. I hope she was audible through the talk, right? Okay. So let us begin with what we need to know if we actually want to help computers understand. First of all, understanding emotion is a very complex topic. Okay? It is probably one of the most complicated topics that we have in current deep learning research. And if you look at the deep learning research that is focused towards computing, you will see that the SOTA models, that whatever we have, they have a very less accuracy. We are not able to build models that can predict human emotions with very high accuracy as of now. hopefully in the future we will be able to do that. That's why we are continuously working towards it. But to build such models, there are some basic building blocks. For example, machine learning is basically an extension of statistics, if we understand it that way. And deep learning is a step above machine learning. Deep learning addresses those problems which cannot be explained by simple statistical rules. For example, understanding how, for example, if we take a picture of this room, and if you want to count how many people we have in this room, now that requires an extensive pixel by pixel analysis, and that is a very complex problem. So we need deep learning techniques for that problem. For example, again, understanding motion, understanding language, visual perception. All of these problems require very complex understanding of the context of the pixel, of the input, etc. So that is why we need deep learning methods and deep learning models to build solutions for that. So now emotion understanding is something that requires visual input as well. You can look at a person's face, you can tell if that person is angry, if that person is happy or not. So we need visual perception as an input to understand emotion, and also language. If we hear someone speak, or if we can read someone's writing, we can tell if this person is angry or not, if this person is happy or not, if this person is sad or not, right? So language and visual perception, photographs, images, anything it can be. So these are the most fundamental input for understanding emotion. And in this tutorial, we are going to deal with it. I'm going to show you how to deal with visual inputs, how to deal with text inputs, and at the end, I've got one small talk on how you can combine both of these inputs to prepare a multimodal model. But that is a very advanced topic, and I did my research in that topic, so I'll talk about that as well. So now let's move on. All right. So you might be thinking like, what kind of software do we need to use for this to do this kind of research? So see, deep learning models are very heavy. At the very core of it, deep learning models, they are basically huge matrix multiplications. And matrix multiplications, they are very computationally expensive. We need to train them on GPUs, and sometimes it takes hours to train one model and get the results on it. But again, you can have free GPUs. I mean, your university might have GPU facilities that you can use for your own research. Google Colab is a very interactive Jupyter notebook environment. They give you free, 16 GB of GPU. Sometimes you get Tesla 4 GPUs, which you can use for your training. There is one platform called Kaggle. It is basically a very big platform for data scientists and machine learning researchers, and they use. They also give you some GPU access, but they only give it to you after you've used that platform for a long time. And of course, there are paid GPU hardware that you can take on rent, for example, cloud services like GCP. Our company uses GCP, for example. And we also have Amazon Web Services, Microsoft Azure, stuff like that. They sometimes become expensive. And okay, and as for the software requirements, we'll be using Python 3.6 and above. Okay, and to build the models, we will be using different and platforms. For example, we have PyTorch, TensorFlow. These are basically platforms that help us build models easier in a very easy way. Okay, so what are the deep learning frameworks? I just told you, right? So deep learning frameworks are basically platforms that provide you APIs to build a model. Like for example, if you want to build multi-layer perceptron, a neural network, for example. Back in the days, in the 2000s, when people were working on deep learning research, writing these kind of machine learning model was very, very difficult. You had to write huge lines of code just to write one single neural network with one data set. It was that difficult. But now there are different companies, like we have got Google, we have got Facebook. They're all having their own research labs, and they're all building their own platforms, which makes this writing code for machine learning model much easier. So you can use any platform you want. For example, we have got KRS, or TensorFlow. TensorFlow actually supports KRS. So if you're using KRS, you might as well use TensorFlow as well. So TensorFlow is very easy. If you're just starting to write machine learning code, it is very easy to write it. In fact, I wrote my first machine learning code on TensorFlow. And PyTorch is much faster than TensorFlow, by the way. And the thing is that PyTorch gives you that level of flexibility when you do it. So, and okay, so that is about this deep learning framework. There are a lot of other frameworks as well. You use very all right. So, any deep learning model has the common structure, and as you can see here, this is pretty much what a deep learning model looks like. We have got a data, and to handle that data, we usually deal with huge gigabytes of data, and we cannot obviously handle all those gigabytes of data at one time. We have to handle them in small batches, right? So this data handler does exactly that. It takes one small batch of data from the disk, it sends it to the model, we train it, and then we take the next batch of it. So it's a repetitive process, and batch integrators is responsible for managing the data. It basically loops over the data in small batches. The data handler sends it to a trainer. I'll explain what a trainer is. Task. Let us focus on this. The task is the definition of our machine learning problem. The problem that we are trying to solve. For example, we are trying to, let's take the example of this tutorial. We are trying to detect emotion from my face. Right? So that is the task. And this task has a mathematical definition of the problem. It has all the details. This trainer is the solution of the problem. We have built a model and we have created some, we have our model description, we have our loss function, we have our optimizers, everything is defined here. Okay, and now this trainer is basically responsible. We have, as you can see here, these are the trainer components: the model, the optimizer, loss function, and the metric report. The model is the description of the model. Okay, how many layers it has, what are components it has. We'll talk about the components of the model in the later slide. But for now, let us just consider this to be the model. The loss function basically tells us how accurate our model is. If our loss is very high, it is an indication that our model is probably not working well. If the loss is low, then our model is probably working well. Optimizer basically is an algorithm which optimizes the loss function. The idea of training a machine learning model is we have our data, we have our model, we have to make sure that the model understands the data very well. And for that, we understand it through the loss function. Like I said, if the loss is very high, the model does not understand it at all. If the loss is very low, then it probably understands the data pretty well. And optimize the task of the optimizer is to minimize the loss. Our target is to minimize the loss, right? So optimizer minimizes the loss. And metric reporter basically tries to understand how accurate it is. What are the accuracy scores? What are the F scores? There are different metrics to determine how good the model is based on our task. So if it is an object detection task, we will probably use metrics like intersection over union or map scores. If it is a very simple classification task, like whether let's say whether I'm a human or not, it's a very simple task. I take a picture and I ask the model to predict whether I'm a human or not. So that is a very simple classification. For that we can use accuracy or F1 scores. Now, now what happens is that basically how the model is trained is that we have got the data handler, we have the data here, we have the trainer here. So the data takes the data goes to the trainer. The trainer calculates the loss in the optimizer. It calculates the loss, and the optimizer wants to reduce the loss in the next step. So it goes back to the next step, takes the next batch of data, takes this loss, takes the previous loss, tries to reduce the previous loss, and then generates some more data. And this continues till we ask it to stop. Let's say, so this one entire process is called an epoch. So sometimes we run the model for 10 epochs, 20 epochs, or even 50 epochs. So in each epoch, it tries to reduce the loss and it tries to increase the accuracy and the F1 scores. After we are done with the training, we export it. We save our model, so we can give it to you. For example, if you want to use that model for some other purpose. Okay, so I was talking about multi-layer perceptron a lot, right? I was talking about neural networks and stuff like that. So this is the very basic structure of a multi-layer perceptron. This, what you can see here, is a perceptron. It's one single neuron. This entire model is actually based on our brain. You see, in our brain, we have got neurons, and each of the neurons are connected by synapses, right? Biology. So, similarly, this is a multi-layer perceptron. These verticals, as you can see, these are called the layers. We have got the input layer, we have got the hidden layer, and we have got the output layer. So this output layer basically tells us. So let's take this example for instance, we are taking some input. We are asking to predict if this is a dog or a cat. So it takes the input, it does some calculations. I'll explain what calculations it does, and then it tells us, okay, it's a dog. The same thing goes for a cat as well. So as you can see that these inputs are basically it takes the input. These inputs are basically numerical inputs. Let's be clear about that. Even when we are taking the images of a dog or a cat, we have to somehow convert that image into some form of a numerical input. We call that embedding, because we cannot deal with images, right? We are talking about mathematical models here. So mathematical models must be numerical in nature, right? So we have to somehow figure out a way to convert this image into a series of numbers. So that number represents that image uniquely. And then we perform some matrix-based calculations, and then we get the output. Okay? Okay. So let us say, so this one is a bit more complex neural network than the previous one. In the previous one, it had only one hidden layer. This one has, I guess, 4 hidden layers. Yes. So we have got inputs here. These inputs are basically numerical inputs. It can be anything: 1, 2, 3, 4, 0, -1, -1, 0. Anything, any numerical input. This numerical input is then passed to the hidden layer. Now, what happens in this layer is basically this. As you can see here, we have got the inputs here, right? It has certain weights. Weights for each layer has a weight of their own. Each weight is basically a matrix. Like I told you, deep learning models or machine learning models have a lot of weight. So these weights are basically matrices. These are numbers. We calculate we calculate basically the result of each output layer of each neurons using this function. So we have this multiplied by this weight, plus we have got the bias. Then this multiplied this multiplied by this weight, this multiplied by this weight, this multiplied by this weight. So we have got basically 4 different multiplications. We add them up together with the bias, and we get the output for this state, this particular synapse. This repeats for all of these. So we have got one hidden layer out. Then we move on to the next. Same thing. This multiplied by this multiplied by this multiplied by this. We have got another hidden layer output. And then when we do all this, and finally we calculate this in the final layer, we calculate the output. So this output is basically a probability, whether or not. If we go back to the next slide, the previous slide. So if you go back to the previous slide, as you can see, it works the same way. If the structure is the same, it works in the same way. What this output is basically probabilities. What is the probability that this image is a cat or a dog? If the output probability is very high, we can, and if it is correct, then we can say that the model is working very well. But if the probability is not very high, if the probability is low, then the model is probably unsure of whether or not it is a dog or a cat. Okay. So as you can see, this is pretty much the design. Did everybody understand the design? Is there anyone who did not understand it or want to explain it? Or do you have any questions regarding the design? Because if not, we will be talking about it. All right. So let's talk about it.
Shanknil, can you just give them correlation of the picture and these things? So if you, because many of the people are may new to the touch and other thing. So what brief thing you can give them so that they can follow. Okay.
Yes. Yes. All right. So if you have all understood this diagram, so what in that case, then you will know that what we basically have is we have some input, we have got 4 hidden layers, and each of the hidden layers has got 5 synapses, and we have got output layer with 1 synapse. Right? How do we write this in code? How do we actually write a code that we can train and get some results? So this code that you can see, this basically is built on PyTorch. We talk about PyTorch, right? PyTorch gives us more flexibility and it's faster. So this is built on PyTorch. You can write this on TensorFlow as well, Keras as well, anything you want, no restrictions. So let's call this some model, some random model. We create a Python class. If you have coded in Python or if you have coded in, for example, Java previously, how many of you have coded in Java? Java. Yeah. Okay. Any object? Do you guys know about object-oriented programming? You know about classes and stuff like that, right? So, right. So this is pretty much that. It is a class. We are defining a class. This class is an instance of NN.W. Basically, we are telling the class that okay, we have to create. We are trying to create a model, right? You guys know about abstract classes, right? Abstract class, yeah, right? So what abstract class does is basically gives us a blueprint of the class. That you have to build your class based on this blueprint. Okay. So that's what we are doing here. We are having some class and we are telling it that we want to build it on the blueprint of model, which means that we have a constructor. I guess you all know about the constructor, right? So constructor initializes the object. So this is the constructor that we have, and here we are stating that okay, hidden layer 1 is a linear. This function is a linear function, right? It's a linear function. You're basically you're having a vector, you're having a matrix, you're calculating this function. It's a very linear function. It does not have any polynomial in it unless you make this polynomial. That's what we have. NN.linear is a linear function model where you take an input, you're taking 4 synapses as input, right? And we are giving 5 synapses as output, right? Hidden layer 1 does that. Everyone is okay with that, right? Cool. Then we go to
Shanknil, can I, sorry for disturbing. The how many of the students know neural networks previously before coming to this lecture?
How many of you have known about neural networks before you entered this school?
Nero tarmoqlar nechta turlarini bilasizlar? O'rganganingizni. Bormi?
Yeah, just a simple tip to understand the neural network. Human brain, there are the neurons, and these neurons are connected each other when a message or the signal is passing. Signal means electrical signal is passing. So they will be fired when they got sufficient information in it. That means the learning things. When you learn, then it will be fired. So that firing will make you to move into the next level kind of thing. So that's a concept in hidden layers explained kind of thing. So we have activation function, right? And then a summation of all these activation functions. These are things, the information you are passing, that is the data. The input layer is capturing the data. The hidden layers will really imitate the human behavior, the brain, the neurons behavior kind of thing. And the exploration is in depth, and this is not a systematic, explicitly explained kind of thing. It is the abstract level. That is the thing Shaknil is asking you. It's a predefined certain the framework. In these things, the different neurons, the activation function will be, activation time will be different, but certain level they will fire, and then the decide that when it fired, it is called as learning things. That's why the learning process is slow. And deep learning, the main thing is a learning process takes more time, because it handles the large data set, and the big data problem is resolved almost by the deep learning. Yeah, this is the generic understanding. And thank you, Shantnil, you can continue.
Thank you, ma'am. Okay, so yes, let's continue. And like I said, it's a this entire whatever is happening here, it's a linear combination, right? Like I said, so we are taking a linear model. We are telling that it takes four synapses input, and it gives out 5 synapses. It's pretty easy. And it's the same for layer number 2 as well. It takes 5 synapses input and gives out 5 synapses and output. Now the number of this input is fixed. It depends on your data. Whatever size of data you have, based on that you will have to fix it. But this, the number of outputs for this can vary. And how many synapses you will have in the hidden layers, how many neurons you will have, that will depend upon your experimentation. You'll have to experiment. There is no right answer to it. Sometimes it can be like I took a random example as 5 here. 5 might not work, 10 might work. We don't know. We have to run our experiments on that. And that's why sometimes machine learning research takes a long time. Just because we have to run these experiments and see which one works better. And sometimes you also use your intuition, like, okay, this seems right. So you go away with it and then you work your way out. So layer 1, layer 2, layer 3, and layer 4. All of these are pretty similar. In fact, layer 5 is also similar. It's also a linear combination. We are taking these as 5 as input and we're taking 1 as output. This one, it returns some form of probability, like I said. All right. So I guess you have understood till here, and if you have any doubts, please you can ask me now. We will have a question and answer session at the end as well. But if you have any doubts right now, just anything you can ask.
I have a question. What's the linear basis as in this linear and then no linear?
Linear? Okay. This basically represents this function.
Is it inside the PyTorch?
Yes. The Python platform. If you look into the source code of this one, it will actually describe this mathematical function. It will run a for loop. It will take all the inputs. It will multiply the input with the weight. It will add the bias and then return the cumulative value. So you can actually go to pytorch.org and you can search ML.linear, and then you can look at the source code of this. You can all see whatever code is used. Okay. So any more questions? If you don't have any questions, I think this had been pretty advanced for many of you, because I don't think many of you have known about machine learning ideas like this. So I will give you some time to think about it, and let's take a coffee break. Everybody use. Yeah, cool. We'll come back after some time and then we can see from you. We have a long way to go now. Hello.
Yeah, Shani.
Yes, ma'am.
Is it 5 minutes break?
Yeah, 5-10 minutes coffee break. Yeah. Professor Dhananjay said that these people are pretty new to this, so if you go it all at once, then they might get overwhelmed. So give them little breaks in between.
Yeah, that will be fine, because later just think, because it's maybe I think many of the people are new to the machine learning things.
Yes.
See, you just can explain them that Python, the Torch is a mainly the libraries, that is methods, the procedures, simple steps, written, explain, all these learning neural network learning principles kind of thing, and that mathematical procedures well written, okay, well written and made as a library function. So when you just call the PyTorch, that is import, you little bit explain more on code kind of thing instead of this thing. So when they come back, so you can make it what exactly the import, right? And then what is the torch kind of thing? Torch is a package of libraries, okay, that mainly work for the this neural network, the deep learning neural. In the deep neural network and the thing, we can implement all the learning principles, right? In the artificial neural network, learning principles are there, and each learning principle have well defined mathematical method, right? Procedure, and that are written and made as available for everyone. Simply just click and use concept kind of thing. Okay, so that is the main the question the student is asked now. If you can explain them, they will clearly understand what the student is asked the question. So his doubt was this thing, whether mathematical things is. So it's because making the comfort and main intention, you have to tell them that mainly they are doing all those things because our main intention is to imitate the human perception kind of thing. So you go on sitting and writing the code for the all the methods and other thing, we will lose the things. That's why they are providing, these libraries are providing, and simply you can click and extract what exactly the behavioral action of the human by the machines kind of thing, so that you can immediately exhibit the concepts kind of thing, right? So you just tell them where they can understand easily kind of thing. If you go in depth of mathematics or in depth of the subject, I think somewhere they lose the they may get bored, right? So it's too much firing of the neurons is the difficult, right?
Okay, I'll quickly come back
So
from the break and then I'll start. Okay.
yeah.
See you. Let's loss function here in the binary loss function. However, let us say we have a picture of this, and your task is to find my face, right? That is an instance of object localization, and this can be a very good loss function, intersection over unit. I'm not going into the details of all this, the mathematical details of all this, because it might be way too advanced for it. But let us continue. But let me tell you, we'll be using these loss functions a bit, and when we will be using it, I will tell you how to use. Okay. So okay, guys, do you remember that model code we wrote a while back? This one, right? Do you remember this, right? Cool. Now let's say we actually want to train it. If we want to train this model, we have to define its loss function, and we also have to define its optimizers, right? Like I told you, we have to define loss function. So, here we are taking that model class that we had defined. We are creating, okay, it's basic object oriented programming. We define a class, now we are creating an object. And also, deep learning models can get really, really heavy. So we need to train them on the GPU, right? So this particular line, model.CUDA, is basically a GPU platform built by NVIDIA. Okay. So if you are using NVIDIA GPU, for example, NVIDIA SRT code or something, CUDA is basically a software tool built on top of that. So what we're doing is basically we're sending the model parameters, the model to CUDA. So it will train on CUDA, on the GPU. This criterion, this is the loss function. We have different names for it, loss, criterion. So basically here it says it is a cross entropy loss. Here is the binary cross entropy loss. There is very minimal difference. So this is a cross entropy loss. We are defining it. You can use any loss function you want. It depends on the problem statement that you're trying to solve. There is no fixed rule for that. And then here we are creating the optimizer. We'll tell you what optimizers are. Like I mentioned previously, optimizers. The task of optimizer is to minimize this loss. This line calculates the loss. This variable or this function basically, this function minimizes the loss. Is that clear? Okay, we have got the model. We are sending it to the GPU for training, for faster training. This calculates the loss. This optimizes the loss. And this process goes on in loop. So in the next loop, it will again calculate the loss. This one will again reduce the loss by some amount. And then it again takes the next data and it continues into the loop. Make sense, everyone? Cool. See, these are the optimizers. We have got, see, this is basically the process of minimization. We're trying to find a local minima on the graph, basically. So there are different optimizers that we use. The most popular, I think, is the gradient descent. If you are getting basic, into machine learning, gradient descent is one algorithm that you will always use. It is pretty simple, straightforward actually. You see this red line here, that is a stochastic gradient descent. It's an improved version of gradient descent. Okay. And we have got stochastic. In the last slide, if you go, see here, I've used the Adam optimizer, right? This Adam optimizer, as you can see, is very fast, but it takes a huge amount of computation. It is incredibly computation based, but it works very well, and it is pretty fast. So for all of these purposes, we use Adam now, to be honest, even though it is pretty expensive. If you can afford that, if we have that sort of GPU, we go for that. Okay, now we have talked about multi-layer perceptron. Now let us talk about the real thing, the thing why you are here for. Understanding emotions from part one, from images and from language, right? So let's say we took an image. We took an image of my face. How do you mathematically represent it? Any ideas? How do you mathematically represent an image? Any ideas is fine, it's all right.
Using geometric shapes.
Sorry?
Using geometric shapes.
Geometric? No.
Geometric shapes simple.
Well, you're talking about the content of the image.
Yeah, we use a mathematical functions for analyzing the face, or it's a human face or it's an animal face.
Yes, what you're talking about is key points and hard concepts. No, what I'm talking about is, let's say, any image. Any image. How can you represent that in a computer? The simplest way is as a matrix. As a matrix. An image is, oh, I think we are on the wrong slide. We have an image that is, let's say, an identification image. So that image will have a length, it will have a height, right? And if it is an RGB image, then it will have 3 channels, right? So can we not represent this image as a, let's say, 1000 cross 1000 cross 3 matrix? Can we have not? We can, right? And each of those, each of the cells of the matrix will contain the pixel values. For example, channel number 1 will have the red pixel values for each of the matrix cells. Same for green, same for blue. And when we combine those 3, we see the image. When we combine the red, green, and the blue values. Does that make sense to everybody? That we can represent an image as a matrix. That makes sense to everybody, right? It doesn't? Alright. So when we are clicking an image, it has a length and a breadth, right? It has a length and a height. Can we not take each pixel of the image and put it into a matrix? So you have an image. The top leftmost point of the image, it has pixel level, right? It has some color, it has some intensity. So that can be represented by a number, right? You can represent intensity by a number, right? So we take that number, we put it into a matrix. We take the next pixel, we put it into another, the next cell. This way, you can take an image and you can put it into a matrix, numerical matrix. Okay, right, cool. So let's say this is our image. Like we said, we can represent an image as a matrix. So this is our matrix, right? How do we analyze this image? How do we extract important features from this? Because at the end, we have to figure out how to predict our emotions, right? So to predict our emotions, we have to understand what is the content of each pixel. The solution is convolution neural networks. Convolution neural networks, what it does is it takes the matrix. Okay. Sometimes we put padding on the four sides of the matrix just to make it equally shaped on all sides. So we have an image. We take one small window. Okay. What you can see is it does exactly what it sees on screen. It takes this, it multiplies with this matrix, and it generates one matrix. Similarly, it goes to the next slide, next window, it multiplies with this, and it generates some matrix. If we split up all these matrices side by side, it gives us a new matrix, right? Now this matrix, this new matrix is called a feature map. Is that clear? Right? That feature map contains very crucial information about the task that we want to accomplish. Let's say if we want to understand emotion. That feature matrix will contain information that will help us understand, that will help the MLP, the multi-layer perceptron that we talked about. It will help the MLP understand whether or not this person is happy, angry, or sad. So here's the thing: the input is, let's say, again, matrix. We have got width one, let's say width, height, and number of channels. If it is an RGB image, this value will be 3. If it is an black and white image, grayscale image, this value will be 1. Okay. And it gives another similar matrix as output. Okay. What it does is, now this is just one iteration here. On an image, we do multiple such iterations and we generate multiple feature maps. Okay. So let's say we take one image, and out of that one image, we generate 16 different feature maps. Now, why 16? There is one separate that is open to experimentation. You can generate 32 feature maps as well. But too much will hurt you, too less will also hurt you. 16 to 32, this is a good number. So we generate 16 such feature maps, and then we take those feature maps, we analyze them, we punch them into a vector, and then we do some sort of an analysis. I'll tell you how to do that. Now again, you can write convolution using PyTorch, TensorFlow, anything you want, right? So okay, let's see what's on the next step. Cool. We are going to look at a bunch of code. Are you guys okay with it? Everything is going good? All right, cool. See, this code, does it look different from the previous code? The line, I mean, the look is, the colors and everything are all same, but the looks, it is different, right? It is because it is written in TensorFlow. So what it does is, see, this line, model is equal to sequential. This function, what it basically does, it tells us that we have to build a sequential model. So what exactly is a sequential model is, we have got one layer. The output of the one of this layer one goes to layer two. This output goes to layer three. So it's a very like sequence like thing. Not every model is sequential. We have models that has one branch, it has another branch, it merges into one branch, and then there are lots of structures like that. This suggests that it is sequential. There are no branches, there are nothing. It's a very plain straight line. Layer one goes to layer two goes to layer three. Okay. So
Excuse me,
okay,
Shanknil.
you guys don't know about Resident 50, right? Resident 50 is one of the most revolutionary versions of CNN, of convolution neural network, that has been used for object detection, not object detection, actually more like object classification tasks a lot. So, as you can see, this layer, this whole thing that is going on, this is one CNN. Resnet 50 uses 50 such CNN blocks, and each block has multiple things. So it's an incredibly complex structure, but it is an engineering model. It can drastically extract features that can help us understand pretty much anything. Emotion, for example, that's what we are going to do when we talk about in this. So, yeah, we are going to actually look at a code that can understand human emotions from faces. Now, the faces, I have made it pretty simple as possible. It has got black and white images, and it will basically take the images and it will predict the output. So, how to actually build a model? That is what we are going to look at.
Yes, Shaknil, one point.
Yes,
Huh. How many of you people clearly understood what is the tensor? And how the slide number 17 picture is related to that thing? So many of you people know what exactly a vector? Vector is clear to all of you? Right. This picture.
It is not clear? Okay, let me repeat. How many of you guys know what is a vector? Yes.
Okay.
Yes.
Shanknil, can I take 2 minutes time?
Yes, absolutely.
See, this picture, Shanknil is trying to explain how an image is a picture. The image is represented in terms of the pixels. There's a point. That point is a x and y coordinator value, right? When a point is represented on the 2D plane, it is represented a value. Those values are both x and y coordinated. This is clear to you, all of you? And how many pixels a given space at a time you are pointing certain space in the image, and you are capturing the pixels, and these pixels parameters we are extracting, right? So if you see into the parameters part, why deep learning is important kind of thing, right? So in a point is represented with the two numbers, but in depth what these two numbers are represented, you can see that a point which color, so that the Shaknil has told you RGB point, right? This is the color coding and the intensity of the color, and these intensities represented in terms of the grayscale. What is this thing? That means each one have certain parameters kind of thing. For example, happy moment, when you are extracting the person is happy, so you just see that what is the lips shape kind of thing, and your the eye lids and eye eyebrows kind of thing. So all these things properly need to be captured. and made available. That is the large data. How these large data are represented in terms of the matrix and a series of matrix connected to that thing. Right? A matrix can be represented in a programming simple vector, right? Vector is a series set of numbers you are representing, kind of thing, with the either one dimensional or multi-dimensional kind of thing. So that entire the number of data and what the data embedded with the features kind of thing is capturing in a given frame kind of thing. And all these values are handled by the your method, the program, right? The deep learning method or libraries and other thing, and get exactly the parameter, the important information, and that information is explaining you that this is a happy face kind of thing. So for that thing, you need to capture a large set of matrix connected series kind of thing is a tensor kind of thing. So that's why that tensor library will have all these functionalities as a libraries. Is it clear?
Clear, right? Cool. All right.
Thank you, Shantanu. Yeah.
Thank you. All right. So yeah, let's move on and let's look at some code. Can we put on that browser? So before we go on to the code, first let me give you a brief idea about what our data set is. I don't know if I'll be able to show you a sample data, but I'll try to show you a sample data. Okay, but here is some metadata about the data. As you can see, 48 cross 48 size images, which are quite low resolution. Okay, when we deal with high resolution images, we have to build larger ones. They take huge amount of time to create. Okay, and they are like pretty difficult. And in fact, the model complexity increases as well. When we have got larger images, let's say HD images, then HD images, they have a lot of pixels. We have to build, more complex models to understand what's in all of them. So for simplicity, it is a very low resolution image, 48 cross 48, and we have got like 6-7 emotions. We have got angry, right? So that's what I'm doing. As you can see, here you can see, we have got a log. So as you can see here, I'm trying to unset and it is inflating on it. If you see the structure of the data set, we have a folder called data. Inside that, we have a training folder. Okay. So when we are building a machine learning model, this is just a recap. The data set that we have is 80% of the data. That's one number. More than 80% of the data goes to training the model. What do I mean by training the model? Reducing the loss, right? And 20% of the data it goes to testing whether or not we give it an unknown value, and we see whether the model is giving correct result, right? That is for testing. So this is the training data set, training folder. This particular image is a sad expression image. So it is put under the folder called sad. So the folder structure is very simple. So we have got the root folder. Inside that we have got the training and testing folder. Inside training folder we have got all the sad, angry, happy, etc. folders. Inside that we have got the image. Pretty simple, right? So let's go ahead and look at. Can I use the keyboard? Is it possible to use the keyboard?
Keyboard, yes.
Okay. All right. So all right. This particular thing is that we are importing all the necessary packages, Python packages that we have, Python packages, libraries. This will be brief. NumPy is basically it handles all the numerical calculations, array manipulations, stuff like that. This is the data frame. A data frame is, you can say, an advanced version of tables. It makes table manipulation very easy, right? So it is often easy for us if we can represent the data as tables. So table manipulation is easy. This is for plotting data, graphs and all. This is also we mostly use it for graphs and statistical image analysis. This is also for those purposes. Let's move on to the machine learning libraries. As you can see, we are using Keras and TensorFlow. Keras. Sorry.
TensorFlow?
Yes. Yes. So we are taking the Keras. We also have the TensorFlow. We are building on TensorFlow. We have got all the. So this is for image generation. You guys remember we talked about data loaders, right? In the architecture, data iterators. I told you you take small batches of data from the disk and then process. It basically does this particular function. Okay. This one, this Keras TensorFlow Keras graphic import ResNet 50. This basically imports the ResNet 50 architecture. ResNet 50 is a huge architecture. So we have already trained the architecture. Some person have already trained it. So we are loading that trained architecture. These are basically different. This is the activation function. We talked about activation functions, right? So this is the activation function. This is the normalization. Normalization, what it does is basically it normalizes. It brings the value between minus 0, minus 1 and plus. Not like the activation. Activation function generates the probabilities. Batch normalization just takes the statistical mean, average. It just takes the average and then brings it to that. Then this I will discuss later. And this is basically the model we are trying to describe the model. This is also for those purposes. We'll discuss this later. These are the callbacks. I'll also explain callbacks later. And this is the Adam optimization. Optimizer we talked about Adam. All right. So all right. Cool. So this particular line of code, what it does is it prepares basically the function of this particular whole line is whenever we are taking the data, whenever we are preparing a model for training, we have to take the data in batches, right? So it basically does that. It takes small batches of data and it sends it to the model for training. This is for the training purposes. This is for validation. Now, what validation is basically when we are training, simultaneously we are checking whether our model is doing well or not. If the training, we expect that during the training, loss function should reduce, right? So, validation is basically during the training process, we are checking if our model is actually learning something during the training process. And testing is after the training process. So when the training is done, we have the model, everything is ready, no more improvements to the model are required. Now we are testing on some data whether our model is doing well or not. Validation is basically if the model is not doing well. Training is basically if the model is not doing well on the training data set, it will try to improve and then check on the validation data set whether or not it is actually improving. Because sometimes what happens is that if you show the model some data, it might so happen that it will learn the data in a way that how do I explain? Let's say I give you some text to me, for example. You can do one of the two things. You can either understand the text, the meaning of it, or you can just learn word by word. Right? You can do either of those things. A model also behaves in the same way. A model can learn the data pixel by pixel in such a way that it will not actually understand the problem that we are trying to solve. It will just learn the data in a way to memorize it. So what happens is that this is what validation helps us. Validation gives us some unknown data and checks whether or not it is actually memorizing the data or it is learning the features. So this is basically a safety net for us. So So here it is. This is basically where we are giving path here, like I told you, this is the training path. And the validation part also takes from the training part itself. The training data, again, like I told you, 80% of the training data goes into training, actual training, and 20% goes to validations. Okay. I told you, right, that the data is sent in small batches. The data is sent to the model in small batches. This is the size of the batch, 64. Sorry. So it takes 64 images, randomly selects the 64 images, sends to the model for training, and then randomly selects another 64 images and then sends it. So that's how it happens in each loop. All right. So yes, this is one sample image. As you can see, it's a black and white image, 48, very low resolution. But you can figure it out that this person does not look very happy, right? Yeah. He's angry. That's why it is under the angry. That's the folder. So what we do here is when we're trying to build solutions for such complex problems, we build our model in a particular structure. It includes a backend, a backbone, and a NLP head. What is an NLP? We discussed, right? Multi-layer processor, neural network. Right? The backbone basically helps us collect features, important features that can, and those features are passed to the NLP, and then the NLP generates an output. In this particular case, let me show you this. Can you please switch to the yeah. Audio is not coming. I think the audio. No. Okay, can you check once? You guys can hear me, right? But I'm not sure if this the people online can hear us or not.
No, his audio is working, right?
Okay.
So now it's coming.
Okay,
Okay, fine.
Can everybody see the PPT?
PPT.
The people, because it's showing you the screen sharing.
Mm-hmm.
You have to switch.
Just seconds.
All right.
Mm-hmm.
Let's go back to the slides. All right. This is an NLP, right? What we do when we are building very complex models for such tasks, we have a like I told, we have a backbone, and we have an NLP head. Say this is our head. This input comes from the backbone. The backbone generates this out. So same for here as well. Let me take this example for now. We have an image. We take an image. We click the image. We pass it to the backbone. The backbone analyzes the image, generates this input. This input is sent to the NLP head. We call this the head. So it goes to the head and it generates the output as, like, let's say here we have got two outputs because we are checking whether or not it's a dog or cat. In our case, we have got 7 outputs, right? There will be 7 outputs. Angry, sad, happy, disgust, whatever. So this structure is it clear? Right? The backbone and this stuff. Same here. This input is generated by the backbone. The backbone's output is passed to here. And then we are passing to the neural network and it generates outputs. Here we have got 1 output. In our case, we have got 7 outputs. Can you switch back?
Switch browser.
Browser.
And this one.
Yes. Cool. So therefore the resonance is actually a big part of all that. In this particular case. So here, this is the code for the backbone. This is our backbone. We are taking the base model. Our base model is the ResNet 50. Okay, we are taking the ResNet 50 base model, and then we are adding some layers. This layer prevents the model from memorizing the data. Okay, we have to put many safety checks on the way so that our model does not memorize it, because that is a very big risk, especially in terms of such big model, such dense model. It's a very big model. That's why. So we take it. Flatten means basically we have got a matrix. We take a matrix and then we flatten it. Pretty simple, right? We take a matrix. We have a 2D matrix, like a square. First row, and then second row, third row, fifth. It's a flatten. That's what it is. Like I said, we have batch normalization, it normalizes the data. So this is our data. ResNet 50, we are adding some dropout. ResNet 50 is our backbone. And here is our MLP. So this is basically an MLP. We are taking 32 layers as it is. We are taking this whatever layers we have, whatever output is generated here. It's a sequential one, right? I said so. Output. So this layer, the output of this layer goes to this layer. The output of this layer goes to this layer, and it goes on. So this portion is our MLP head. Basically, we are taking hidden layer. 32 outputs we are having. Remember, in the first code that I showed you, it takes two inputs, right? One is the number of input and the number of outputs. Right? Here it takes only one input. It automatically calculates the number of inputs. That's the difference. So the number of output for the hidden layer is 32. We perform the same process here. This is the activation function, the radio activation function that I told you we use a lot. And again, we are creating another hidden layer with 32 units. Same process as before. And then we create another hidden layer that has 32 units. So basically, we have got three layers that has 32 units. Okay. And then we have the output layer which has got 7. Because we have got 7 different emotions. We have to calculate the probability that which one of these has what is the probability of this emotion being sad or angry or disgusted. So that's why 7. Is it clear? Anybody any questions? Cool. So let us look at the models now. See, if you want to visualize the model, this is what the model somewhat looks like. Like I told you, it's a sequential model, so it goes in one statement. The output of this layer goes to this layer and this layer and this layer. So, as you can see, this is the ResNet 50. These two are the ResNet 50 backbone. Okay, and after the ResNet 50 backbone, it goes to the, and this is our multi layer process. This portion is the multi layer process. Okay, so it's a very sequential input. It goes. It's actually a very big model, and at the end, last we have got the output. Yes, this is the output. It takes input as 32 and then output as 7. Okay, so this is pretty clear, everyone. It doesn't. You want to explain it? All right, cool. All right. So I'll do a quick recap once again. This is our diagram. Okay. Our diagram. The output of the diagram goes to the or MLP backbone on the head, right? So this base model is our ResNet 50. We are taking the ResNet 50, that is our backbone. We generate the output of ResNet 50. We take the output of the ResNet 50 and we pass it into our MLP. Okay. ResNet 50 is very good at analyzing pixels. Very good. So that's why we are taking this. That's the simplest reason. So we are taking this, and then this is our MLP. This MLP has hidden layers, like I said, layers in between. So first layer has got 32 output, 32 units as output. Second layer also has 32 units as output. Third hidden layer also has 32 units as output. All of these three has got 32. And the last output layer has got 7 units as output. Why? Because we have to predict 7 different dimensions, right? So that's why we have got. Now, if you want to plot this, it will generate a graph like I showed you below. See, this is pretty much the model description. As you can see, this is the resonant 50 now. 2 plus 2 plus is returning a matrix. Okay, it's basically returning a matrix. It is also returning a matrix. And last, it is at last. If you take this matrix, if you flatten it, it will generate this way matrix, right? It's a three-dimensional matrix, and it is, and the output is a 1-dimensional. And then this is, it takes then the output of the hidden layers 32, 32, 32. As you can see, this is hidden layer number 1. This is hidden layer number 2, and last is hidden layer number 3. All right. Let us then.
Shanknil, sorry, can you just give them what is the importance of NLP involvement in deep learning? Yeah, so that they can understand clearly what is these all the layers and everything. Because the depth of knowledge required to understand a language by human and how it is incorporated by the machine, just so that they can easily follow the whatever you are explaining. Yeah, thank you.
All right. So that was how you actually write the model in code, in actual code, instead of just designing some stuff. If you want, you can actually I'll make this entire code public. You can run this in your own browser. You don't need any fancy or anything. You just take any computer and run this, and you can actually see the result of yourself. But if I try to run this right now, it will take around 1 hour. So let's get into that. So this, as you can see, is where we're training the model. Model.fit. We are passing the training data set, we're passing the validation data set, and we are training for 30 epochs. Do you remember what epochs are? Do you guys remember what epochs are? Epoch is basically one loop of training. One loop of training. So we are looping for 30 times. With 30 times we are going over the same data, we are learning different features each time, and then we are trying to minimize the loss. As you can see, here at the beginning, the loss is 1.837. And our accuracy is something. Now, if you go down, as you can see, you see the loss is actually reducing over time. This is what optimization is. We are going for epoch 1 as we are going, and each day the loss is reducing. It is a pretty long training process, but let us see. But you guys did see that the loss was reduced, right? So if you go towards the end of the training process, on the 30th epoch, the loss we are expecting to be around 0.001 or something. That is an optimal amount of loss. So this version of code is basically a bunch of code that will show you the plot, how the accuracy and the loss is changing over time. Because that is a very important metric to understand how we are trying to how good the model is fitting.
Exactly. How much left?
We are left.
Long, right?
Yeah, a bit. Because I have to cover languages.
No. Because we don't have time. When we have to finish?
After probably 15 minutes.
15 or 50?
Yeah,
15. 15. Can you conclude 15?
Well, we have to miss out on languages.
Just remove it because and speak a little bit slow. You're speaking very fast. Go ahead. Okay.
All right. Okay. look at
1
this,
to
as you
3
can
is
see,
the lunchtime.
this is the number of people. Okay. On the X curve, we have got 0 to 30. We have 20 to 30
Presentation
calls.
is speaking,
Okay.
Yes, yes.
And the accuracy started from
But-
very little
is going on, right?
and then it jumped over time.
Now
So it is
is
improving.
your
This is going
screen share is
And this one
move the
is
other
this is a
stage.
validation. Like we told,
after
we also
yeah.
conduct many tests while on the training process. So the validation accuracy has remained almost the same. It didn't change at all. So similarly, loss, as you can see the curve, loss will have been decreasing more.
And
That's what optimization is.
each presentation.
Again,
My
AUC is
YouTube
also
video.
another metric.
Okay. Can
We
you
use it
Yeah.
for to understand the performance of
in
these
the
problems.
Yeah.
So yeah,
YouTube
that's
video
pretty much
live
about
also.
how you can
You are
detect
saving, right?
the
Recording.
topics.
Yes, yes, recording.
That
Yes.
is-
Zoom recording.
So,
Yes.
I will make, so this is actually a public course. So if you guys want, you
Presentation,
can have the link.
I will move
And you can actually
copy
run
this
all these
same
codes and see how this is working out.
Later.
We test it out.
later from
So, Since we are low on time, let's move to the next thing.
Yes.
Okay.
in presentation.
Presentation.
Continue.
So that was on images. So language detection from images. We took an image, we converted it into matrices, we analyze the pixels, and then we send it to the NLP to generate some data. But how does language work? We can represent images as matrices by default. It's a very default setting. We can represent it as the intensity of the pixels, for example, as matrices. But that is not the case with languages. Languages are words. How do we represent languages into matrices? We have to somehow represent them into matrices because it's a mathematical function, right? So we use language models. So what language model does is that it takes the words. We have a huge dictionary of words for any language. It can be English, it can be Uzbek. We have a dictionary. And each word, it takes each word, it analyzes it with the dictionary, performs some very deep analysis, like you can see the process going on here. This is an LSTM job actually. So, and it outputs some numerical number. We have got language models like LSTM. This is an LSTM actually. So we have got recurrent neural networks. We have got BERT, and all of these language models are designed in a way to understand the meaning and context of the language. Because to understand emotion, we need to. And see, most of the languages fail at one particular.
So do you guys know HTM.Rigno, right? Please tell them. This key function. This is for
BERT we have the next slide. We are working with BERT.
Just give them the full name and speak slow so they can catch it. Okay?
I'm trying my best.
Yeah, tell them. Slow.
So LSTM basically means long, short, term, memory.
Yeah.
Okay. So
Again, 2-3 times, and then go slow, then they will catch. Teach less, make better. You understand?
okay. All right.
Yeah.
So what long, short term memory does is basically, let's say we have a very long film. And what usually happens is that for a model starts to read from word number 1 and goes to the last word, and each time it tries to understand what the sentence is trying to say. What happens is that if we forget what basically happens is that when we are talking about very long text, the model often forgets what was in the beginning of the sentence, right? So this long short-term memory, this architecture solves exactly that. It takes the memory, it has a long memory, long-term memory, and it also has a short memory. The short-term memory understands the words and how they are arranged, the neighboring words, how they are arranged.
That camera.
The long-term
Camera.
memory basically
Is
understands the entire meaning
Yes,
of it,
No.
right? So that is one language model. And at the end of
This
it,
camera.
it gives us some numerical value. Okay, so that meaning is
No,
represented
sorry,
in the
YouTube.
matrix.
YouTube.
That is the output.
No.
And again, it is a bunch of
Yes, yesterday.
matrix of
No, tomorrow
That's
will
what-
be connected to YouTube. Go. Tomorrow.
So
How about afternoon?
long short term memory and retention internet. These are
After
basically the
the-
versions of the same.
Today
The same
afternoon,
design, they have
and,
different
enter the YouTube. In Zoom videos.
basically. What happens is that in both of these videos, they understand the meaning of the sentence,
Okay, that's
but not the context. Understanding the
I have
context of the
recorded
sentence that is
Zoom.
doing, and that task
This
has
also
been
recorded.
solved
Yeah, yeah.
very recently by college. So this is the architecture. It is a very complex architecture. I'm not going to discuss what is the architecture of God, but I'm going to tell you how it works. It takes this entire language. Is there an audio issue?
Audio working? No.
Sorry, sir.
What
Other
God
voice is disturbing regular lecture.
also understand from
Kindly.
what context it has been sold. Are we clear on this? So when I'm talking about context, it means there has been some reference. Let's say we are talking about sports team. So we understand that okay, we are talking about this in context of sports, right? So that is what I'm talking about context. So but understand that it is a very recent model, it was introduced in 2018, and the reason why it does great for emotional understanding is because BERT understands language, it understands the context, and it can also generate a very big matrix of the input language. So whatever text we are giving as input, at the end we are expecting a matrix. The matrix which we are generating is quite big in size. If I'm right, it probably is 728 cross 1 size matrix. And that matrix we can feed it into the MLP head and we can calculate our emotions. It's pretty simple that way. Now, BERT is a very big model, and there are different versions of BERT as well. We have got this is the BERT base. There is a larger version of that. It is a larger model. It takes larger time to train. We have got Roberta, Alberta, but these are various different versions of BERT. You can say. We take the base model and then we find it based on that. And we have seen PyTorch and we have also seen TensorFlow, right? This time we are looking at Hugging Face. It is also another platform, but Hugging Face makes dealing with BERT very easy. That's why we will be using Hugging Face. All right. So here you can see this is one little animation that I've made. You can see we are giving the text input and it is giving us some emotion, right? Surprise. Okay, this is a very surprise. Wow, this is so beautiful. And again, it is another, let's say, another text that again, if you click on compute here, it again gives some emotions as output. Sometimes the emotion might be good. Sometimes the emotion might not be very accurate. Like I said, that this is a very complex problem. Okay, we are still trying to figure out how to understand human emotions in a very good way.
Okay, great. So this one is the bundle of example, right?
Yes, it's a version of what I think this is.
So they teach you 2-3 algorithms. One is BERT. So one example is that what types here they are typing. Okay, whatever you type, I just made a text data. From text data, they are collecting the information different like anger, fear, neutral, joy. So if somebody is chatting, you can see that he is happy, good, or this kind of thing. So this is example of chatting, texting, right? Like this. And video, tell them video.
And this is also very useful.
You have to finish 2 minutes. Only 2 minutes. Tell them 3 examples. Text done, tell them video and audio.
We have covered
Just example.
images.
Yes.
So this is also very useful because we have this can also take emojis as input, and it can predict the emotion from the emojis, right? So We can also take, for example, audio, like Professor Dhananjay was saying, you can take audio input as input and then you can analyze the emotion from audio as well. How do we do it with audio is, we take the audio recording, we calculate the different features from it, like for example, MFCC. And there are a bunch of features, if I remember, there are 8 audio features that we can calculate. We pass it into the same backbone, similar backbone. We analyze the backbone and then we generate the output from it. So that covers audio as well.
And also audio to text automatically we take out.
Yes, audio to text, we can take out the text from the audio. See, this is a text-based model, right? But this text we can get from the audio. If somebody is speaking some audio, we can use the transcription APIs, for example, Google Transcribe, speech to text, stuff like that. We can generate this text by ourselves, pass it into the same model, and create this result.
Which one algorithm we use for that? Algorithm name. Audio to like
audio to speech. I think we use FFMEG for audio slicing, and there are Google transcription and Amazon transcribe APIs. We have used those APIs in my research to work it out in the same way. We extract the text from the audio.
I'm speaking, each word will convert texted to the recording, right? You can see the YouTube has option already. You can click and there are the script coming. From those scripts, using same algorithm again, you got text from audio. Then it will tell you the emotions of that person when he is speaking.
Even your mobile phone does the same. If you have Apple phones, you have a CD, or you have for Android phones, you have for Google system. It does the same thing, and they probably even analyze their emotions as well. That's a very important data for Google and Apple.
So nowadays the company is already making this kind of smart mobile apps. You can practically test by yourself. Okay, but those are very simple way they are providing free of cost. But as a researcher at back end, we do to create new algorithm every time, because we collect data from so many people. Now here, for example, 50 people are sitting. Everybody's mindset and data are different. Once I got your mindset and data, I can predict about you so very well. Only AI platform can do based on this algorithm. Okay. Similar, I can collect your data, then I can predict more data. But if I'm collecting all data, then predicting accurate but not 100% accurate. Are you getting my point? Right? Now I'm analyzing 50 people's different data, same pattern, then telling them about the mindset. Okay, so now here is the camera. It will tell you how many percent you understand about this whole class. Okay, because as I mentioned before, face expression, speech, text. This is the conclusion of all this lecture. Okay, I just want to conclude because this time is longer. All right. So that's why I just take it from here. So I hope you understand this all material we will upload at the YouTube. Okay. As well as I will give to your professor. Okay. When you have interest, open and check by yourself. Okay. Today, tomorrow, day after tomorrow, give them your email ID.
Yes.
Last page, maybe, right?
I have not seen my email ID, but
so in the email ID, send him email, or we have IHCI group. Okay, so in IHCI group, Telegram group, in the conference website, you will get that link. Join that group, ask question as much as you want. Related to artificial intelligence, related to human computer interaction. Who likes your question, we will reply that. Okay. I hope you understand, right? So whole lecture was just basic introduction about that. Okay, speech, audio, and text. Okay, and for speech, audio, text, he has shown you some example experience. He was waited for speaking part, but his PPT will tell you more better. Okay, he is. Actually, also, as I said that, like you guys, So he don't know how much you understand. He was doing his job. He was so much focused to finish on time, to finish this whole slide. But objective is that you have to understand. I want to make you motivate to study the topic. Okay. So when you saw robot is speaking and sensing, it means because this kind of young researcher has made algorithm and it's working backend, the backside. He was telling you so many things. In the backend is working, right? You using so many words. In the front, the camera, it looks just normal camera, but data goes to the computer. And in the computer, all process going on. All right. So I hope you understand and enjoy this session. Thank you so much. Please join from tomorrow our conference. Here is one man. Can you see Professor Nagamani is here, this lady. And
Yes.
she is also behind this whole PPT slide, whatever he presented. She guided him to prepare this whole lecture, whole PPT. Somehow she wanted to come here, but she has some health issues.
Yeah.
She didn't come because of this problem. But soon she will come and meet you guys. Maybe next year also some conference and something. Okay, so you can meet her and see the professor in India, University of Hyderabad. It's in South India. Okay, so there are lots of participants, other students. They are participating different part of the country, and I hope you enjoy this whole session. Please join afternoon session. We have also another speaker, and he's going to talk about the what I told before. Can you anybody remember?
Aerial detection.
One more time.
Aerial detection.
Area detection for what?
Aerial detection.
Suspicious people. Suspicious means bad people. I'm a bad guy, criminal. My behavior, gun. He will detect and tell you he's bad guy. So police will bring him. So his solution is very much good for use for metro. You have metro, right? You also say metro. What do you say? Subway, metro subway. So you put in the metro subway camera, and they will catch bad people. So the police can catch him before he enter to there, because in the metro, thousands of people come same time. Police is difficult to check everyone. Camera will check. And then police tell algorithm will tell 5% people or maybe 10 people are bad. So police only focus on that 10 people. Right? So he is going to talk about that. Thank you so much. Go and have lunch.
Thank you.
Thank you.
Thank you all.
Let me start with my topic of tutorial is like deep learning application for object detection in aerial images. So I'll be giving a very comprehensive overview about deep learning in the aerial images as well as remote sensing images also, because nowadays the next generation objective is to use satellite images with good resolution. And in fact, we are already on the track, because we are using drones, we are using UAVs for detecting so many objects of interest. Now, these objects of interest can vary with the within the frame of civilian application as well as military applications. Since I am from defense background, I'll be more focused on the general moving objects. So moving objects means they can be tank also, they can be car also, they can be motorcycle also, they can be long vehicles also, and so on and so forth. So basic point is whatever we can achieve through aerial images, we can also achieve using satellite images. So basic point is that my title is land cover and land use classification. These are the broad. Yeah.
Yeah, please hold. Okay, so please go slow. After 15 minutes,
Okay.
most of the students going to join, because now they are in the class. Okay, Gaurav, listen carefully. So just talk to them normal and tell them after 15 minutes, other students going to join. Then we will start proper. Just talk about the motivation about their topic, talk about the basic introduction, and talk to the audience. 10 to 15 minutes.
Okay, okay,
Next
fair
session,
enough.
okay? And then
Fair enough, fair enough.
start your
Okay, fair,
session after 15 minutes. All right?
fair enough, Dr. Dhananjay.
Okay.
Fair enough, Professor. Thank you. So now in general, why are we so interested in deep learning and why are we so interested in object detections? See, deep learning has, and why deep learning? Because deep learning has this nagging ability to extract features from images. It can learn feature extraction. And that is how, since uh, in the basic of deep learning is somewhat complex neural networks aligned in form of various sort of models. Now, most of these models currently have been used in a pre-trained manner that we also known as transfer learning. But it is not imperative that we can only use pre-trained models. We can also use a model which has been trained from scratch. You and myself, or anybody else for that matter, can design his or her own neural network modeling. So basically, that is called in the DNN arena as convolution neural network. Since the most of the focus that you must have attended previously is also known as also we are focused on convolution neural network. So convolution neural network has this ability to read the images, to extract what are the most fundamental and important features in the images, and those feature descriptors can be used by us for various other purposes. Now, one of these purposes is object detection. Now, why deep learning has come up to this particular stage? See, what my research and what I have done is to decipher the behavioral pattern of humans walking on the street, behavior pattern of the people who are driving their cars on the street. Now there are two perspectives to this. How are we going to see the people? The normal perspective is to use a CCTV camera. Now CCTV camera is what? CCTV camera gets the images with the perspective of human eyes. There was a classic case of Google Lens which flopped abruptly because they tried to create so many perspective images from different perspective and not from human perspective. The human perspective was one of them, but they used animals, they used bags and so on and so forth, which created so much of confusion in human minds. So human minds are aligned to the most common used human eye perspective images, and that is being uh, rationally taken by CCTVs. So when CCTV records the frame from the front, we usually have uh, have a classification problem, a multi-classification problem, or a binary classification problem. Now, these problems needs to be deciphered accordingly, and what I believe that it needs the very fundamental classification is of binary classification. If an event is there in the image, or if the event is not there in the image. Supposedly, if an suppose we talk about an object car, if there is a car in an image, we label it, we save it in a folder called car. And if there is no car in the images, we save that folder in the image in the other folder. Now, this is a very, very simple binary classification that is uh, being used to address using convolution neural network classification algorithm. Now, most of these DNNs, deep neural networks, and convolution neural network, the pre-trained models like ResNet, like MobileNet, like VGG16, VGG19, ResNet 152, DenseNet 201, and so on and so forth. There are so many models which is being used in connection to, because pre-trained, they are pre-trained models, so they have this ability to basically align themselves according to the feature descriptors. Why deep learning? Because uh, the deep learning, the term comes because we can add so many number of layers, and these layers can help us to identify, to learn most of the difficult non-linear features. Now, this is a very significant step that needs to be done. So, since Dr. Madhusudan, Dr. Professor Dhananjay has requested me to go slow for few minutes so that people can join post 10 minutes. So I am just giving an overview about what are the things that we need to look at the overall perspective using deep learning.
Okay, I got
Why
it.
deep learning? Okay. Why? So that's why I'm not changing these slides. So, so it's just a basic thing that deep learning has this ability to learn complex non-linear features from an image which is difficult for a human mind to read. And this is the crux of all the deep learning environment, all the deep learning uh, theories and algorithms and so on and so forth. Also, now since the world has known that deep learning is in such a wonderful state, so they have decided to use so many frameworks which has made deep learning very conductive in all the scenarios, whether it is an RGB image, whether it is a multispectral image, whether it is a hyperspectral image, whether it is a more complex satellite images, whether it is a SAR images, satellite aperture radar images, and these all kind of images can be used with the help of deep learning frameworks. Now, the two most popular framework that has been introduced in the literature and in the development processes, TensorFlow and PyTorch. Most of the time, I go for PyTorch as well as TensorFlow because these frameworks has given us so many inbuilt functions, so many inbuilt libraries, so many inbuilt data sets, and they have given us the ability to ingest our own custom data set into their own library. And that is how we approach a simple binary complex problem, binary classification problem, and multi class classification problem. So this is how we go about it. So secondly, why my title is Land Cover and Land Use Classification using Sentinel-2 satellite imagery with deep learning. See, uh, since most of the people in this particular conference and otherwise also have this uh, idea about deep learning and their classification and object detection image. So I wanted to give it a more different and complex perspective, and that complex perspective is how are we going to approach aerial images which we get from Google Maps or satellite images which we can get from free satellites like Sentinel-2, Sentinel-1, uh, uh, and these satellites called Maxstar, who has recently released photographs of the Russian bridge that was broken in a particular Ukraine attack. So those are the things which we need to cover up. So it's imperative for us to amalgamate deep learning technology, and deep learning technology has use of simple neural network, use of combination of neural network, use of transformer, use of variational autoencoders, use of convolution neural network, use of deep neural network, and last but not the least, ensemble them. So supposingly, if we have three algorithms to solve a problem, we can use all three in the end by merging their results accordingly. And that is we call as ensembling algorithm. So ensembling is also one of the finest techniques which has increased the accuracy over the year of most of the deep learning algorithms. So individually they have performed well, and combined with ensembling algorithm, they have performed even much better. So why do we need to decipher like land cover, and why do we need to have land use classification? See, most of the global world needs to be identified with respect to what kind of land resources they have among themselves, whether it's food, whether it's mineral, whether it's built up areas, whether it's river, whether it's vegetation, so on and so forth. So if every country or every state has this opportunity to actually know what percentage of their area, of their country or their state or their city or their district has this particular combination of the percentage of vegetation, the percentage of built up area, the percentage of rivers. This can give us a very fair idea about how to distribute, what is the distribution pattern among the cities and in the vicinity of the cities also, so that a proper planning can be done. Are you there, Mr. Madhusudan?
Yes, I'm here.
Okay. So that's why it's a brief introduction, you know, and so that is why we have given this land use and land cover. It is a very fundamental. It's a very fundamental thing when we study remote sensing images or satellite images. And one of the most prominent problem that is solved using remote sensing images is LULC or LCLU. Both both terms denote to land cover and land use, or land use land cover. They are used interchangeably. And since Sentinel-2 is written here because it gives us free satellite images. And most of these satellite images are huge in sizes. So they need to be downloaded, they need to be pre-processed, and there are specific softwares for that which are very costly. And then there is a open source stream which carries on with the open source stream, open source software, and we use it. Most of the researchers around the globe are now focused on using open source elements for describing their problems among these satellite images, or a, a higher resolution RGB images, which is the exact uh, current study of drone images or UAV images. Now, these drone images are exceptionally critical to any country now. Now, what we have seen from Ukraine-Russia war, or for that matter, what we have seen in the border areas of the of the country that from I belong, we have seen use of drones. We have seen use of swarm of drones, and we have seen drones to capture images of enemy locations, or we have seen drones to capture the location of terrorists, so that the Indian Army or whatever anti-terrorist operation can be executed. So, and similar, whatever the advantages that drones are providing to us, the same sort of advantages are being provided to other party also. So, just we need to we need to make sure that we need to make sure that we are more advanced on the usage of drones and what we can achieve further by classification of the images that is being transferred or recorded from drone. Now, there can be two approaches of resolution of uh, satellite images or aerial images. Now, the first is whether to conduct algorithmic operation on the drone itself while it is flying. Normally, a drone flies for 25 minutes in the air and it has another backup of one battery. So, most of the time, if with the help of two rechargeable batteries, it can fly up to 1 hour or 50 minutes, most probably. And that can give us an entire, it can cover around 20 kilometers by 20-kilometer area. And it can give us vital information to the person who is sitting at a central location. And when most of the drones are now, whenever they are being almost on the verge of dischargement, they come back to their central location. There is a particular alarm which goes off and they come to their last location or the initial location. So let me proceed. Madhusudan, should I proceed now? Na?
Yeah, I think you can continue. You don't need to break.
Okay. ठीक है. So we need to focus ki why actually we need this LULC. So the abstract itself says that many government programs are taking enormous efforts to make satellites free and open source in order to bring innovation and entrepreneurship. Now, what does this particular statement? Now, the three important words are called satellite images, which is free and open source. Even when we download images from ISRO, Bhuvan, these images are not very crisp in resolution. They don't offer very good resolution, and that's why uh, satellite images of higher resolution becomes a costly affair, and that's how uh, satellite images are so costly. So, in order to get great insights and knowledge from this satellite data, we have to segment and understand it for further studies. Now, what does it mean? Now, if we want to segment it, that is another beautiful application of deep learning, because deep learning is not only used for image classification or object detection, it is also used for object segmentation and what we call as panoptic segmentation. And that is what Tesla cars used in their automatic cars, because they use multiple cameras to segment various objects in real time to uh, to process the feed. Now, I was talking that whether there can be two approaches. The one approach is to solve the uh, object detection or LULC problem at the edge devices like drone itself with an embedded Jetson Nano hardware embedded drone, but it will consume more battery and it will then fly to a lower height. But that is the pros and cons of drone images or aerial images hardware. The second is, and which is more preferably if it is not a very real-time operations, the second algorithm focuses on recording the images, and then forwarding it to a central location or a central server where already a model learned on those objects has been deployed. Now these videos are then extracted frame by frame. Now every frame, there can be so many algorithms for extracting frames, whether we want frame every second, whether we want frame every 5 seconds or 10 seconds or 15 seconds. Now the developer has to take a call on it, because somewhere you don't need to lose out important information. So these frames are extracted, and then these frames are hit. They are hit on the model, and then we get the results. So that is how we approach, and those results are then returned in a JSON form or the image form. And this cloud-based architecture can be integrated with the edge devices called mobile devices. Nobody would want a bulky device nowadays. They will always want a lightweight devices, and with the help of IoT, they can be taken anywhere, any day. So, so this is being used by many domains and so on and so forth. So such a type of task is land cover classification, which comes up and automates the process of identifying how the land area is used. Now, almost all the domain in the world uses deep learning techniques to improve performance, and deep learning is most of the time is implemented in two beautiful languages called Python and R, and they are used worldwide over, and uh, they have so much support of open source, and they have so much support of uh, executability and robustness and scalability also. So now introduction. Now this is an introduction. What type of these can be called an abstract aerial objects, because when we are talking about objects, then we become very specific, whether it is a tank, whether it's a vehicle, whether it's a car, whether it's a van, whether it's a motorcycle, whether it's a train, whether it's a ship, whether it's an aircraft carrier, and so on and so forth. And these are very specific types of objects, which is also being uh, developed algorithmically and taken care of. We first create a data set, then we annotate the data set, and then use a proper framework, which I have already mentioned, TensorFlow and PyTorch. These are the one of the best frameworks that has been used all over the world. Now, since not to suppress ourselves on very specific objects, we have taken another case of abstract objects like highway, like crops, like industrial cover, like river, like residential, because these are the things which are of utmost importance from the sky. Now, supposingly, uh, if you get in the what we have seen in the recent Ukraine and Russia war, that most of the missiles are not targeted over an individual objects. They are targeted over individual abstract objects which has a high value. Now, supposing like an industrial complex. Now, suppose a thermal plant or a nuclear thermal plant or a bunker, so which again comes into the category of construction area, built up area. And they usually, most of the military conflicts usually avoid residential area, which is highlighted here. So how does the army knows about what to avoid and what not to avoid, where are the rivers, where are the crops, and what to target? Now, see, this is the specific objective of what to target and what not to target in a military domain. And if we think about it in a civilian perspective, then we can have key what are the percentage of vegetation, what is the percentage of residential arena, what is the condition of rivers, what turns does river change its classes, that is also mm, calculated using change detection, how much industrial expansion has been there in a city or in a state, that can be highlighted using satellite images or remote sensing images. So two specific sets of abstract object detection or classification can be done, and one domain is a civilian domain, in the another domain is a military domain. So these two domains, they can be used by their individual contributor and their individual user. So basically LULC is based on Sentinel-2 images. It can be any satellite images, but I have taken Sentinel-2 because it is free. And patches are extracted with the purpose to identify the shown class. Now, patches, when I say about remote sensing images, we uh, we know that uh, they have huge sizes, 2 GB, 5 GB, 10 GB, and when there is a constraint in computing power or or on the edge devices, then we need to break down those satellite images, and that is called tiling. And there is a very good open source library, GeoTile 0.2.4, the latest version, which does the work in Python. Absolutely beautiful. And it it actually breaks those images, huge satellite images, into those tiles. Now, ultimately, these images are usually broken into 64 by 64 images, or 128 by 128, or 256 by 256, because their dimensions are very high. They are almost 9,000 by 12,000 resolution images, the whole images, and which needs to be broken off with the help of these softwares. We can also write our customized tiling software also, tiling breaking software. And when we usually tile the images, then we perform image enhancement or image classification like we do here, and which I'll show you in my Google Colab notebook. And then it shows how do we go about it, and then we classify it. And when these patches are classified, now then again it is stitched together, and that process is called image mosaic. Okay, now the two specific, I hope I have made myself clear. Two specific functions. One, image breaking into tiles, perform whatever operations, deep learning or enhancement or pre-processing, any sort of operations on those tiles, get the results and restitch them. The process is known as image mosaicing. So this is how we approach for all the satellite images. This is the basic framework of uh, object detection, also abstract object detection, also abstract classification also, and this is how you approach remote sensing images. Now, I am talking about, because one thing I should make very clear, that these images can be of various bands. They can be multispectral bands. Since we are accustomed, the humans are accustomed to RGB images, red, green, blue. Now, these red color has a particular band. It's called B2, I believe. B2, B3, and B4. These are the three bands of multispectral images. So whenever a satellite images comes up, since we are focused on these RGB images, we extract the particular bands, and then we get the image which is known as RGB images. Because there are so many other bands also, which are known as infrared, near infrared, and so on and so forth, and which humans are not very accustomed. So, since we are accustomed for RGB images, we convert those remote sensing images into RGB images and then use it for our own training and classification purposes. So, this visualization highlights the classes annual crop, river highway, industrial buildings, and residential buildings, and so on. So now, since I have given a particular introduction regarding that, uh, I should now introduce you to a particular data set which is very, very common and which is very, very useful in applying the concept of LULC on satellite images. Now, this is a novel dataset based on Sentinel-2 datasets, satellite images. And see, now here I have mentioned covering 13 spectral bands and consisting of 10 classes with overall 27,000 labeled and geo-referenced image. Labeled means we need to label it. What does this piece of area belongs to? What does this piece of area belongs to? And so on. So that it's basically we are covering a supervised learning. That's why we are targeting as a labeled data set. And what does georeference mean? Every point on that image has a latitude and longitude which can be fetched. Most of the time, this latitude or location data is embedded into your uh, images, which is also known as metadata. So the georeferencing and labeling is one of the classic significant important step of this data set. So again, a significant difference from previous data set is that presented satellite images data set is a multispectral. Since RGB is using only 3 bands out of those 13 spectral bands. That's why normally human beings usually and visually are more comfortable in RGB images. And so multispectral covering 13 spectral bands in the visible, near infrared and short wave infrared parts of the spectrum. It's also all a spectrum. So this particular image can explain you that a satellite gets the image of the Earth, and most of these satellites are geostationary. So they revolve with the Earth, and geostationary orbit is around 36,000 kilometers from the Earth. So there is a patch, which patch is being thrown into a neural network, and then it classified as industrial area. So that neural network is the key. How are we going to train it, and how are we going to get the results? So below illustration shows an overview of the patch-based land use and land cover classification process using satellite images. So a satellite is what? It scans the Earth to acquire images of it. And this is why it scans every 24 hours most of the time. And there are satellites, military satellites or spy satellites, which scan almost 6 times every day for the same place, and it can be pointed on the Earth station. So a satellite scans of the Earth to acquire images of it, and patches extracted from these images are used for classification. Now, these patches are used for classification. They're also used for change detection. And that is how we were able to see what is happening, or what is the volume of destruction that has taken place in war between Russia and Ukraine, or for that matter, with any two countries. We usually take those satellite images, we then change. If we attack, if any country attacks any other country with a missile, so if we want to see the difference, what does the missile have created, the exact process is called change detection of the particular place which is being captured by satellite. So the aim is to automatically provide labels describing the represented physical land type or how the land is used. For this purpose, an image patch is fed into classifier. Now this classifier model we need to train. And then we get the classification of the image patch. So Eurosat is the first large-scale patch-based land use and land cover classification dataset based on Sentinel-2 satellite images. Every image in the dataset is labeled and georeferenced. Eurosat has the RGB and multispectral version of the dataset. Overview of the sample images of 10 classes. The image measure is 64 by 64 pixels. Each class contains 2,000 to 3,000 images. Obviously, we need to have most of the time while working on deep learning projects, we need to have balanced data sets. And whenever we have an imbalanced data set, then we have to apply certain strategy to adjust the weights. So in total, the data set has 27,000 georeferenced images. Again, satellite scans the Earth to acquire images of it, patches extracted, and classification carried out. The aim is to automatically provide labels describing the represented physical land type or how the land is used. Satellite scans the Earth to acquire images of it, patches extracted, and so on and so forth. So again, the satellite It has 13 spectral bands, where the 3 bands are of a, like, for example, B01, B9, B10 are intended to be used for correction of atmospheric effects. The remaining bands are primarily in every band in a multispectral or a hyperspectral. They can be used for various different purposes, like for creating vegetation index, for creating water index, for creating road index, for creating specific types of road index. So whenever we apply that threshold to the image, we get what type of area is there behind the satellite images. Each satellite will deliver imagery for at least 7 years with a spatial resolution up to 10 meters per pixel. Now see, the Eurosat has these particular classification: industrial buildings, residential buildings, annual crop, permanent cover, river, sea and lake, herbaceous vegetations, highway, pasture and forest. Now, see, this was the introduction of Eurosat, which will help us to give us the abstract object on a large patch of satellite images. Now we need to combine it with this recipe of deep learning. So what does deep learning add to the stack? Deep learning has brought about a breakthrough in different areas of AI, such as detection and identification of what? Images, people and sounds. In fact, they are being used for so many purposes. The latest is diffusion models, which has been trained on Hugging Face and what we call as OpenAI Playground, DALI, and so on and so forth, which has a which is a tremendous text to image generation models. So why does the word deep? Deep indicates an increase in the number of layers where a model. That's why ResNet 152 or DenseNet 201 has more number of layers, which a model uses one or more hidden layers is called deep model. So that's why they are called CNN models. Transfer learning, as we have already told you, it uses a pre-trained model which has been trained. Now, uh, just to make sure that you catch this moment, uh, the pre-trained model trained on images cannot be used for pre-trained model for audio files per se, because both the domain is different. One of the domain is images, the other domain is sound. So what we need to have in our mind, if a model is trained on RGB images, it should be used for most probably these RGB images also. Is it okay, Madhusudan? Are you there, Madhusudan? Okay, I'll continue. So here we use deep learning along with transfer learning to improve the accuracy and also make the training faster. We'll work on PyTorch as the framework for our deep learning model. So we use also RGB as a pre-training models are easily available in the RGB format. Now, I'm coming to why this LULC and remote sensing and images with the help of deep learnings, what objectives they can solve in the global matter. See the first example, and these are taken, the credit goes to Ujjwal Gandhi, who has worked hard in the spatial domain, and he has recently given a seminar on Google Earth Engine, and which has given so many lots of insights over how to use this remote sensing and deep learning together. So I have taken some cues from his lectures, and that is how I'm approaching this. Why LULC can be a very, very good thing for a global domain. So basically, it's an inundation and vegetation dynamics of upland lagoons. Now, there are certain wetlands which provide some ecological services like water storage, flood mitigations, and habitat. So, remote sensing using the historically deep Landsat dataset provides a means to quantify vegetation and inundation trends over time. This is important. So that is how first we classify into vegetation and inundation region, and then over a time series, we calculate the percentage changes in the vegetation and inundation areas of any geographical region that we can think of. Again, why are we studying? Why are we studying this particular thing, abstract classification? Because it is used for monitoring forest disturbances drivers in near real time with sentinel data. Now, normally, all over the world, we assume that forest land should not be encroached or forest should not be disturbed. But sometimes people, for their industrial expansion, they usually uh, expand their industrial activity or civilian activity in that domain. Most of these activities are like agriculture activities or road development or selective logging or mining. Now these are the things which disturbs, which are actually a disturbances with respect to forest area. So tropical deforestation and forest degradation are increasingly being mapped with the use of near real-time forest disturbances alert systems. So, however, such systems do not define the underlying direct drivers of the detected disturbances. This particular classification of any geographical area or containing forest can be a boon for a better maintenance of forest. Now, these are the ideas for budding PhDs and postdoc, which can thoroughly look into SAT images with respect to ecological issues of forest. Now, another important which needs focus on the global scale is the soil information. What type of soil is distributed in any country, and then a mapping has to be made with the respect of soil type and the type of vegetation it can be comfortably grow. So soil information is fundamental for a large range of global applications, including assessments of soil and land degradation, sustainable land management, and environmental conservation. Suppose a particular piece of land for last 10 years has been giving us a good crop, and suddenly for next 2 years it didn't perform well. What could be the reasons? Apart from uh, apart from natural reasons, it will also point out to the fact that a land or soil degradation has occurred and we need to do something to increase the cultivability of soils. So basically, the whole world is mapped into soil grids, and it's a global product that fulfills two main goals. It's a source of consistent soil information to support global modeling, what type of crops are modeled across the world, and it supports complementary information to support regional and national soil information products in data poor areas. How much industrialization, how much vegetation, how much river, how much uh, thermal nuclear power plants are distributed all across the globe. What are the ramifications? What are the ecological ramifications? What are the industrial ramifications? We all need to get from the integration of remote sensing and deep learning. Again, it's again a very beautiful application, automated landslide detection. Most of the people living in hilly areas must be aware that what landslides can cause catastrophic uh, and permanent damages to human lives as well as the structure around us. So if we can have automatic landslide detection, we can actually prevent the loss of vegetation and change in ground surface texture. Now, these are the filter images to it creates pre and post event collections and apply terrain correction to sentinel images. Terrain correction will be a module which needs to be developed from pre and post landslides of the same area and create differences images by subtracting the pre and post event composite. Again, the concept of change detection comes and automatically the map the landslides from different images using a simple machine learning classifier. So a new near real time, again, a new application, a new real time deforestation warning system using a hybrid thresholding deep learning approach. Again, previously we discussed about forest disturbances. Now we are discussing about deforestation warning system. And again, satellite images are used and find deforestation candidate by using a spatially variable NDVI threshold approach. Now, this is what is NDVI threshold approach. These are the certain algorithm and formulas which uses the spectral individual bands from multispectral images, and they create a threshold. And when an image is passed over those thresholds, the highlighted areas beyond those thresholds are uh, highlighted. And again, change detection are done over those highlighted areas. And then we confirm the deforestation by using deep learning, whether in this case is resident 50 to discard false alerts coming from flooding, drought, and fire. So deforestation warning is absolutely important because it can give us the cues towards flooding, drought, and fire. Another global thing which we need to focus on the amalgamation of deep learning and remote sensing images or aerial images is land surface temperature for greening initiative. Most of the that is a common term of global warming. So land surface temperature helps us to define the radiative skin temperature of the earth, which in turn could assist us in identifying hotspots in any region. So that is how we approach land surface temperature for greening initiative. And remote sensing techniques in Google Earth Engine are used to retrieve LST, which is land surface temperature, from a combination of thermal infrared sensors and operational land imager of Landsat satellite images. Now, if we can focus on everything here, it can give us the global warming initiatives of all over the globe. So again, another very interesting application which comes from deep learning application on aerial images and satellite images is mapping irrigation practices using Google Earth Engine machine learning. So irrigation causes groundwater depletion, water pollution local to regional climate change. The information on irrigation practices and their changes over time is needed for assessing and managing limited water resources such as location, technology, frequency, efficiency, water use, and water withdrawals. The image on the right side, these are the remote sensing images. It goes into a deep learning model and then it classified as what kind of irrigation practices are being performed abstractly in an area satellite region. Again, a new era of hyperspectral remote sensing for agriculture. Again, it focuses on building a hyperspectral image library. Hyperspectral means more than 13 bands. It can have 500 bands, it can have 600 bands, it can have thousands bands. And crop types, and from these spectral library, we actually calculate the crop type, growth stages, and growing condition, and so on and so forth. So using these libraries are very, very important. So it proposes hyperspectral vegetation indices for estimating crop biophysical and biochemical characteristics, use machine learning algorithms to classify crop types, and so on and so forth. So that gives you a perspective how to approach aerial images abstractions from using deep learning. Since I'll not go into the deep learning because you have already had sessions on tensors and deep learning, reinforcement learning. So you can be well aware of how to go about it. So the references are Eurosat. It's a novel dataset that has been, this I'll be using for Google Colab and for land use and land cover classification. Now the credits goes to Ujjwal Ghane, which is on the Twitter with the ID of @special thoughts. Amazing human being, and has given us so much of insights into usage of and amalgamation of remote sensing and deep learning with the help of Google Earth Engine and ML Workshop. And again, an important and significant resource for anybody looking into deep learning application in aerial images remote sensing images. Rob Markole, satellite image deep learning. It's a GitHub repository. Amazing scientist from UK, and it has given so much of we have so much to learn from it. That, it's amazing. So this brings to the actually the introduction part of what we needed to expect from these aerial abstract object detections. And since I was not very keen on focusing on very small objects, which I'll also cover, I'll give you a brief about it. But this particular thing happens. This is very significant, so that you people can actually think about in the larger and broader terms of satellite images uh, and usage of deep learning over it. This is the next generation which is coming up. And in near about 10 years, we all have access to satellite images. We need to be prepared to focus on large scale, global scale, vegetation scale, farming scale, temperature scale, water scale, all over the world. So this brings to the end of the first presentation. Dr. Madhusudan, are you there?
Yes, Bhaiya, I'm here.
Acha. So now I'll go for the second presentation. Now this is a Google Colab library which will tell us about how are we going to use Eurosat datasets. So when we now Eurosat dataset can be downloaded individually from its website also, and now TensorFlow has also embedded that into its own TensorFlow.tdfs dataset, and it can be used from there also. So we have downloaded Eurosat, and then now we are unzipping it. I hope people will be aware of how to use Google Colab with their Gmail account. See, these are the classification. Sea lake 3000 files, forest cover 3000 files, river 2500 files, highway 2500 files, herbaceous vegetations. Now see, we can have so many different kinds of vegetations also which can be clubbed. We can go further into it also. We have industrial 2500 files, we have annual crop 3000 files, we have pasture 2000 files, we have residential 3000 files, and we have permanent crop. Overall around 27,000 images. We want to check the size 64 by 64. We want to plot. These are the number of images in each folder. We want to see some sample. So these are the samples: sea lake, forest, river, highway, herbaceous vegetations, and so on and so forth. Industrial, annual crop, pasture, residential, permanent crop. Now, we define the training directory, we define the testing directory. We have taken batch size of 64. The more the batch size, the better it is. And when the data is scarce, then we can down sample the batch size to 4, 8, or 16. Number of classes as the number of folders in the length of folders. There are 10 classes. Input shape is already shown 64 by 64. Class mode categorical hai, it's not a binary. We are converting it into dataset and keys. It shows which number of images, what type of annotation it has. Now we split the datasets into test size, train size, and it's a random shifting. Around 20,250 training files belonging to 10 classes, and using 18,225 files for training. Similarly, for testing purposes, we have class names, annual crop, forest, herbaceous vegetation, highway, industrial, pasture, permanent crop, residential, river, and sea lake. Then we can plot those. auto-tune is a feature of TensorFlow. See here, we are defining the models, and you must pay attention to this line number 14, where tf.keras.layers.dense has 10. Why 10? Because the number of classes which needs to be classified is 10. If the number of classes would have been 3 or 30, then this number could be changed to 3 or 30 accordingly. So how much we are expecting for a multi-class classification? The number of classes should pass into last layer, the dense layer. An activation function is softmax. The optimizer is Adam. The matrix is what? Accuracy. And I'll be using, let's suppose, just for the sake, the one epoch. So single epoch has given me the validation accuracy of 52%, 0.5250. Now let me increase it to 5. That is how you experiment with this is a Euroset dataset. If you have your own custom datasets of your own classes, please go ahead and use this Google Colab for training purposes. One thing you must make sure that whatever is the environment in Google Colab, the same environment should be in, if you are using this Jupyter notebook, converting into Python files. So the requirement.txt should be generated. The same Anaconda environment should be in your laptop or a DGX server, and then you need to train. So after 5, the validation accuracy is 72.72%. So I go ahead. Now suppose I make it 10. Normally we use for 10 epochs. This is the standard. As we can see, now the validation accuracy has increased to 78.7. And if we increase this, we can have more number of accuracy. So now model.evaluate is a function itself defined with the model, and we pass this test ds we already defined above. Then we evaluate on training dataset. So the accuracy on training dataset is 80.23. This is the model summary. You know that it's a 2D convolutions, and most of the convolution neural network use pooling for information maximization. And then the last layer in the end we use for flattening the datasets, and then we use dense layer. Then we use dropout for dropping out information which is not very convenient for the model. And the last is dense layer. And the last but not the least, you just save the model as euro.5 into your. And this model is actually being, you can see the model is euro.5, and you can see the size 376.4K. And you can use this model as an inference model in your software. So normally what we use, when a satellite images comes, we break into tiles of 64 by 64, because 64 by 64 is the size that we have used in training. Now these tiles is being hit to this euro.h5.model, and then the result is saved. So we classify all the tiles of the huge satellite images, and then we combine it. The combination of those classified tiles is known as image mosaicing, and then your final image gets ready for usage. Now a report can be generated of percentage and so on and so forth. What percentage is deforestation, vegetation, what percentage is sea lake, what percentage is herbaceous vegetations, and people can use, civilian can use accordingly, military people can use accordingly. So this completes my abstract aerial region detection on Eurosat dataset, which has been made with the help of Sentinel-2 satellite, and I have demonstrated how to integrate deep learning on remote sense images or satellite images for a larger abstract region perspective, and this can go for a long way. How you use, how you visualize the usage of not only RGB images but also multispectral images. Dr. Madhusudan, are you there?
Yes, I'm here.
Okay. Now I'll come to the final part.
Okay, go ahead.
So since I have given a vast and large perspective over, is it visible now? This screen?
Still, we can see only Google Colab.
Dr. Madhusudan?
Yeah, we can see the Google Colab. We are able to see Google Colab one.
What actually I have used here is basically with the perspective of drones, because drones can go up to a limit of 20 kilometers to 50 kilometers, and these are the well crafted aerial images on which usually civilian and military applications are being performed. So just in general introduction, that why drone warfare is necessary, and because of cheap hardware and huge potential, small ammunition, drones can create panic and havoc in military areas, and so on and so forth. Positive capabilities also in civilian domain is to see about whether the roads are good, whether any event, any civilian event is happening in a controlled and organized manner. So different perspective to the aerial images. So the present work is related to object detection, and drone surveillance can help us to be vigilant about this new asymmetric warfare and civilian application also. So I'll be quick on this because most of the things that I've already covered in remote sensing images. The application will detect any object of interest. The images may be geotagged or may not be. Normally in a military areas, army areas divided into sectors, these geolocations shall be mapped onto a map. An alert is sounded for the objects of interest. And after detection of these objects, object tracking can be done. Now, these all things has been done in Python application. These are the drones. And why in military domain? Because we need to have intelligence, coordination, fire control, over the ridge, and so many ISR related activities. So traditional warfare is drone level warfare. Traditional warfare was between space, air, and terrestrial. But now things have changed, and we need to have a newer perspective on drone level warfare or a low flying warfare. So ISR activities, intelligence gathering and smuggling of weapons and so on and so forth needs to be stopped. This is how satellite or aerial images can be taken from drones. Now this is the architectural framework. An input is generated. We have a CNN-based object detection model of detection, classification, and segmentation. And we classify the objects with geotagging and we can give the alerts. Again, this is a video analytics engine which can be combined with the drones. These can the control server can be at the edge, but it is very difficult to process the images in the real time. So most of the time it is backed up in the cloud itself. Our experiment focused on the development of convets from scratch and extended to pre-trained convets. We curate a drone-based dataset for various types of drones and so on and so forth. So automatic target recognition, classification, tracking of specific targets, spectral analysis, real-time generation of various surveillance, user-defined alerts, and change detection within an area of interest. Most of the time, this particular aerial object detection is focused on object detection. So normally it's an example. What I have used is YOLO 5. The full form of YOLO is you look only once, And currently YOLO 7 has been accepted in the programming field, but the most stable version is YOLO 5. And normally we curate a data set, we divide into testing and training folder, and we annotate it, and then we use it in the YOLO 5 format with the help of the framework of YOLO 5 that PyTorch has provided. So this is how after post training it looks, and we can see the number of the number of classes that we have used for is car, truck, van, long vehicle, bus, airliner, propeller, trainer, chartered, fighter, other, stair truck, pushback truck, helicopter, and boat. These are the things which can be detected. These are the most common objects of civil and military interest both. So this is the result that we can see. We can see car, we can see long vehicle. These are all object detection of aerial images using YOLO 5. And for YOLO, for further information on YOLO 5, please go to the GitHub page of Ultralytics, which can help us, which have so many tutorials on using YOLO 5, YOLO 6, YOLO 3, YOLO 7, and so on and so forth for object detection in a CCTV. I have used it for aerial images. These are references, and thank you for giving your time to this. To further show something, so here I have developed a model, and you can see this framework, this web framework is called Streamlit. It's an open source software, Python software, and it has been extremely helpful for you choosing a model. I have in the left pane I have chosen YOLO 5. There can be other prediction model. I have chosen YOLO 5S. Small, S means small model, and I have taken an image and see the results. You can see the airliner are detected. The numbers are confidence factor. There are chartered flight propellers, airliners, chartered airliners, and so on and so forth. So these are the things which can be used for uh, detection of aerial objects, and this all has been made with the help of YOLO 5, and the data sets that has been used. Again, I'll give you I'll give you the data set information also, but I can give the link to it. These are the data set from Stanford. It's from a Stanford data set, and it's an aerial images data sets. Normally, YOLO 5 has been used on COCO, Common Objects Dataset, COCO 128. The pre-trained models are trained on COCO datasets. Now, the user has to just use its own customized datasets, and I have used aerial images datasets on aerial images datasets on Stanford aerial images dataset, and these are readily available on the Stanford data websites. So this brings me to the end of my presentation.
Thank you very much, Dr. Gaurav Tripathi.
Yeah, see, these are the images. I have uploaded the images, and see, you can see the results of plane. You can see the results of plane, and so on and so forth. So this brings me to the end of this presentation. I hope I have done justice to this IHCI platform. Thank you for the IHCI platform, which has given me an immense opportunity to present my perspective of deep learning and remote sensing images and aerial objects. I hope it will be beneficial to the students who may listen, who are listening to me right now, or who may listen to me in the future with respect to this video lecture that is being recorded. Any questions, Dr. Madhusudan?
Yeah, I was going to ask about the audience. Anyone has any questions, please ask to Dr. Gaurav. Ajay Sanknil, are you there?
Okay, I hope I have done justice, and it's
Yeah,
been
it seems
it's
like
been
no questions there. So
yeah.
I'm just wanna be introduce you first. Like I need to introduce and before the starting the presentation, but like of the
Sure.
students, I just wanna be introduced to you that you guys, this is Dr. Gaurav Tripathi. He's a senior scientist at the Central Research Lab in BEL, Bharat Electronics Limited in India, and did his PhD from the his master's from the IIIT Allahabad, his specialization in artificial intelligence, Indian Institute of Information Technology in 2007, and he completed his PhD from Delhi Technological University, India, and currently as already mentioned, he's working as a senior scientist in the Center Research Lab. So I just going to appreciate and thank you very much, Dr. Gaurav, to giving to this
Thank you,
nice
Dr.
and
Mansoor.
useful talk for two audience. I think it will gonna be helpful for everyone who's attending this conference, your tutorial. Thank you very much.
Thank you so much. God bless.
So and Ajit or Shwapnil, are you there? Anyone is there?
Okay, but Dr. Mansoor, I'm signing off. Thank you.
Okay, thank you, Dr. Gaurav. IHCI to 2022. Any administrations is there? Sorry, Professor Nagamani ma'am. I think Gaurav has already left. But as he mentioned that he's taking the all captures, image pictures from the Stanford database from there.